Let's review a bunch of stuff regarding polynomials. First thing, before we get into it, I want to go back and talk about a couple of simple definitions of some vocabulary words that are used over and over again in algebra class, and we're going to need these more for this for the chapter on polynomials and also for beyond for rational expressions. Factors is something that you've heard of before. And I'm going to give you a very simple, straightforward definition for factors. This is something that I'm hopeful that you can remember. You should put this on a flashcard because it's pretty important. And here's what the definition is. Factors are things that are multiplied. That is a pretty fundamental definition. Now, if you go look it up, you'll find fancier definitions, but I think this is a pretty darn good definition. And we need this vocabulary word. We're going to be using a lot, and when I say it, it'd be nice if you knew what I was talking about. To go along with it, there is this other word, terms. And again, this is used a lot. So it'd be nice if you knew what it was, and putting it on a flashcard and going through and looking at it over and over and making sure that you know the difference between factors and terms, that'd be great. Terms are things that are added. So why is this so important with regard to polynomials? Well, the deal is this. The definition of polynomials, the definition for polynomials, or polynomial, is this. I'm gonna provide it in a very simple way with these two words: many terms. That's what a polynomial is. It's something with many terms. So it'd be kind of nice if you knew that terms were things that are added together. Now you'll notice that I use the word things, and the reason I do is because sometimes things that we add together are numbers, and sometimes they have variables also. In other words, sometimes we have several things multiplied together, several factors, and then that becomes one term, and then we add several terms together. So for example, let's take a look at something. How about if I have this? Negative 3x squared plus 2x to the fifth minus 7x plus 14. This is a polynomial. And it's a polynomial that has, well, I don't know about many, but it has several terms. This guy here is known as a term because it's being added to this guy here, and it's being added to this guy, and it's being added to this. There are 4 terms in this polynomial. Now there's several things that, oh, and by the way, if I take a look at any one, and let me go ahead and write, these are terms. If I take a look at any one of these terms, any one of these guys is known as a product because there are several things multiplied together, and the result of multiplication is called a product. So if this is a product, then it turns out that the individual parts of this term must be called factors. There we go. So this has a factor of negative 3 and a factor of x squared, and technically x squared is x times x. Over here we have factors. Here's a factor, 2 is a factor, x to the fifth is a factor. Again, x to the fifth is kind of like 5 factors, but we'll call it a factor. So anyways, again, I wanted to clarify, here's several factors multiplied together. And then when I add that to something else, this whole thing becomes a term. So this whole guy is one term. All right, let's go on. As long as I've taken the time to write out this polynomial, let's discuss a couple of other things. This polynomial is not in proper order. Normally, we'll rewrite this polynomial to put it in the proper order. We put the highest power variable first, or the highest power term, and then we'll put the lower powers after that, negative 3x squared minus 7x plus 14. And then when we look at this highest power variable or highest power term, we'll use that to determine the degree of the equation or the polynomial. In this case, the degree we would say is 5. And then also another thing about that is we'll also make note of the leading coefficient. The leading coefficient is the number in front of the variable with the highest power, and I'm going to abbreviate coefficient. And in this case, the leading coefficient is 2. So hopefully you can see that there. There's the 2, and there's the 5. And that's where we get the degree and the leading coefficient. And hopefully you remember that we had some discussion about end behavior and degree and leading coefficient. Another thing that we need to discuss regarding polynomials is that since polynomials are things added together, but it's not everything that's added together. So let's take a look at some things that are not polynomials. So we'll say, is this a polynomial? And we'll say no. So if one of our terms in our polynomial looks like this, in other words, it has a negative exponent, then we'll say that whole thing is not a polynomial if this is just one of the terms. If one of the terms looks like this, 1 over x, or if there's a variable in the denominator of any fraction in the polynomial, we'll say no, it's not a polynomial. And by the way, you might recall that this is directly related to this, because if I have an x in the denominator, it's like having a negative exponent. And then something you might not have expected. If we take the square root, or any root, and if we have a radical over a variable, and it's one of the terms in our polynomial, then we don't have a polynomial. In other words, if we have several terms added together and one of them is this, then technically it's not a polynomial. Let's take a look at some things that might fool you into thinking that they're not a polynomial, but they're actually legitimate. So let's say if we looked at these and we asked the question, does this thing make it a polynomial or is it not a polynomial? We'll say yes, this is part of a legitimate polynomial. If I have negative 3 as a coefficient in front of x squared, yeah, that's a legitimate polynomial. Negative 3 is not the exponent of the variable. And if I have a fraction in front of the variable, like 2/7 x, that's a legitimate term in a polynomial. You can have fractions as coefficients. You just can't have the variable in the denominator. And finally, if I have something like 3x times the square root of 2, that's a legitimate term in a polynomial because the variable is not part of the square root. So let's clarify a little bit here. It turns out that what we're trying to get at is that variables in a polynomial should all have exponents that are positive integers, or also known as whole numbers. Variables, if you have a polynomial, variables have exponents that are whole numbers. And that's kind of an important concept. Whole numbers are numbers like 0. You can have x be to the power of 0 in a polynomial. That's just fine. You can have 1, 2, 3, 4, 5, 6, any of those numbers, but we cannot have negative numbers as exponents, and we can't have variables in the denominator, and we cannot have variables under radical signs. Let's talk just for a moment about degree of a polynomial. I said earlier that the degree of the polynomial has to do with the exponent, the highest value of exponent of any variable in the polynomial. But there is a slight exception to this, or a special case. It's when you have a situation that looks like this. And let's label this special case. When you have something like x cubed times y squared plus x to the fourth, at first glance you might think that the degree of this polynomial is 4, because the highest power variable is 4. But this is a special case. And what the situation is that because we have the x cubed times the y squared, we consider this polynomial to have a degree of 5. And we get that degree from adding the 3 and the 2. By the way, let me go ahead and back here and let's make that degree 7 for that previous polynomial. We get the degree of 5 here by adding the 3 and the 2. Now that's weird because normally you're not allowed to multiply. We don't combine together these exponents when we multiply. For instance, if I look at x cubed times y squared, it does not equal x to the fifth. And it certainly does not equal y to the fifth. And I don't know what that is. And it does not equal x to the fifth, y to the fifth. So please, don't confuse this with any of these. But again, as a special case, when we're trying to evaluate the degree of a polynomial, if I have 2 or 3 variables multiplied together, I have to add their x. And by the way, let me be clear, if I have 2 or 3 variables multiplied together, they are considered one term. And if I have several variables multiplied in one term, then I will add their exponents to find the degree of the polynomial. Now, this is a special case. It's not something that you should be concerned about normally, but if you do run across a problem like this, we have to add these exponents for degree. Not when we're not in any way combining those two factors together. Before we go any further, I have to talk about the big four. This is a huge concept, and I want to make sure that you folks get this down. Roots and zeros and x-intercepts and solutions. With regard to polynomials, these things are synonymous. In other words, they mean the same thing to some degree. Let's talk about how they're similar and if there's any exceptions. First of all, if we take a look at the graph of a polynomial, here's our x-axis and here's our y-axis, and if we have a function that goes something like this, here's our polynomial function, it turns out that wherever we have crossings of the x-axis, those guys are known as roots or zeros or x-intercepts, and also they can be known as solutions. Let's take a look at why that is. The reason why these roots and these zeros and these x-intercepts are also known as solutions is because they occur when on the line that's known as the x-axis. And at the x-axis, the x-axis is where y equals 0. And it turns out that when we want to solve a polynomial, what we do is we set y equal to 0. And that's why when y equals 0 and we get these x-intercepts, that's why they also happen to be solutions. So if I set my polynomial equal to 0, and I solve whatever values of x that I get, x equals whatever, that'll be my x-intercepts. Now, in this particular case, this polynomial does not match with this graph. I just put the graph up and the polynomial as examples of where you can find the roots and the zeros and the x-intercepts, and why we also call them solutions. Because when we set y equal to 0, we get the roots or the zeros or the x-intercepts. One of the things that was mentioned in the chapter on quadratics was that you can have, if you have a parabola that looks like this particular type of parabola, where the graph has two x-intercepts, it will have what's known as two real roots or two real solutions. If you have a graph that looks like this, where just the vertex is on the x-axis, then in that particular case, we end up with just one real root or one real solution. And then if we have a case like this, where we have a parabola that just never touches the x-axis, that's entirely possible, then we have what's known as this has no real roots, because there's no x-intercepts. However, it does have two complex roots. And the reason that we get two complex roots, well, maybe not the reason, but one of the things that shows that we get two complex roots is the quadratic formula. You might recall from the quadratic formula that it's x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Well, if it turns out that this guy in here, if the discriminant under the radical gets us is a negative number, then we're going to have a plus and a minus complex root. And that's what happens with a parabola like this. Now, I'm going to expand on this idea of how the graphs are related to the roots in just a second here. But I wanted to remind you, with quadratics, we saw in the chapter on quadratics that you can have two real roots, or one real root, or zero real roots. And one of the things that I want to point out here is that quadratic equations are second degree, and or also known as degree 2. And it's not just a coincidence that they're second degree polynomials, and at the same time they have a max of two real roots. Now, they can have less than two real roots, but they'll always have at least two roots. So here's two complex roots, and let's see here. And here's two, well, maybe not always have at least two, but here's two complex roots, and here's two real roots. In this particular case, we can also have one real root, and this guy does not have any complex roots. One of the things I haven't talked so much about is how the degree of the polynomial relates to the number of roots. So in the last slide I showed that if you have a quadratic with a degree 2, you could have as many as two real roots. Take a look at this polynomial. It has there's one real root, 2, 3, 4 roots, also known as zeros or x-intercepts, and so as a result, we could say that it's very possible that this could be a fourth degree polynomial. And since I see that there are no other x-intercepts, I'm pretty sure this is a fourth degree polynomial. In the past, we discussed that this would be an even degree polynomial because it goes up on both ends, and we also said it probably has a positive leading coefficient because it's sort of a smiley face polynomial. So there we go. Leading coefficient is positive, so it's going to be happy instead of frowny. But we didn't talk about the degree and the roots. Let's take a look at some variations on this. This particular graph shows a similar polynomial to the one above, except this one only has two real roots. But that doesn't mean that it's just a second degree polynomial. In fact, it's definitely not. Second degrees are parabolas, and this is not a parabola. What happens with this guy is that this could very well be, in fact, I think this is a fourth degree polynomial as well. The only thing is that it only has two real roots. That means that it also has two complex roots, and that would give you your four total roots for a fourth degree polynomial. So this guy up here definitely is degree 4. We can be sure of that. And this guy here, we have two real roots, but there are more roots for this guy for sure. And we'll take a look at the actual polynomial and talk about that in just a sec. Let's take a look at a fourth degree polynomial where we can really see the roots as far as solutions. We'll take this guy, and by the way, let's set this equal to 0 so we can actually see solutions. And this guy, because this 2 here is half of the 4, we can use the x factor on this guy. Now that doesn't mean that it's factorable, but we can certainly try. What we'll do is we'll take the 2, put it down below, negative 3, and it's probably going to be like a 2 and, what are we going to add together to get? Let's make this how about a 3 and a 1? I think that'll work nicely. So we'll go 3 and 1. If I add 3 plus negative 1, I get 2, and 3 times negative 1, I get negative 3. So this will get us factors of x plus 3 and x minus 1. But you'll recall, because we have this fourth degree, this fourth power, this will have to be x squared, and this will also be x squared, and they're still equal to 0. Remember that when we factor, this here is, well, I should say this here is still the equivalent of this guy up here. So all I'm doing is substituting this back into this original equation, so I still have the equal 0. So anyways, back to our factoring. Zero product property is what I'll use to solve, and when I do, I got to factor a little more. We've got x squared plus 3, but this is a difference of 2 squares, so that's x plus 1 times x minus 1. And so this gets me x equals 1 and negative 1 very quickly, or vice versa. And then here we've got x squared plus 3 equals 0. Remember, zero product property. If something times something times something equals 0, then either this is 0 or this is 0 or this is 0. So if I have x squared plus 3 equals 0, then x squared must equal negative 3, and that means that x equals the square root of negative 3. And we always make that plus or minus when we're solving for x. That turns into x equals plus or minus I root 3. Now what this means is that I have 4 solutions, and that's what I was saying earlier, is that this is a fourth degree polynomial. It's fourth degree, and as a result I can have up to 4 roots or solutions. And in this case I have the 2 real roots, but since I only have 2 real roots, I also happen to have 2 complex roots, and that adds up to a total of 4 roots. So it turns out that when we're looking at polynomials, if you look at the degree of a polynomial, that tells you the maximum number of real roots. So the degree is equal to the max number of real roots. And that's worth making note of. Okay, I have a ton more things to share, but I think I'm going to cut for right now.